So I've become rather interested in the kinds of things that seem to be durable about our profession, the kinds of things that seem to be sort of fundamental and don't change. And if I'm honest, I think I was in a bar somewhere talking to somebody about this kind of idea, and they said, well, what sorts of ideas would be true in 100 years' time? And I thought, that's quite a good idea to think about. So that's what this presentation is if I'm right about some of these things, what are the kind of durable ideas? What are the sorts of things that are going to be true about our discipline in 100 years' time? And that should say something about those things, because that means that they're important. It means that whatever it is that we're doing, because the technology will be different, it will be changing for sure. But what does that mean? And I suppose one way to start thinking about this, if we're going to think about what technology, software development is going to be like in 100 years' time, we might as well think about what was it like 100 years ago. And I think most of us in the room probably think nothing. There was nothing going on there. But that's not quite true if we think in terms of information systems. 100 years ago, there was this thing. This is the Hollerith machine. And this was a physical device that was used in the US Census to try and calculate and count the population. This is a computer. This woman was what was called a computer at the time. She was working to compute the results based on the Hollerith machine. And on the table there, you can kind of see there's this device. This device was a punched card machine. This is a much more modern punched card. This is from the 60s or 70s or something like that. I couldn't find a picture of the Hollerith punch card, but the principle was the same. You got this punch card, and the hole meant a 0, or a hole meant a 1, and the absence of a hole was a 0, kind of thing. That sort of model. What's really interesting is that if you want to try and encode the algorithm that was built into this device, you can do it, and you can write it in SQL, and it looks like this. This is what the Hollerith machine was doing, and I think that says something kind of interesting. We got this device that was a mechanical device based on punch cards, and we can write the algorithm in SQL, and that SQL looks vaguely like the kind of stuff that we would write. There's something, it seems to me, that's fairly fundamental about the level of granularity with which we need to express ideas in order to make them computable. We've tried for decades to raise the level of abstraction. We've had a couple of attempts that have worked significantly. The step from binary encoding things with punch cards or switches on the front of a device to higher level languages where we could capture those in first, things like Fortran and COBOL and Lisp was a significant one. That gave us a huge step forward in our ability to encode more complex problems. But since then, we've had the odd little blip here and there, but on the whole, I don't think progress has been quite as significant as we thought. Of course, there's progress, but there are some fundamental things that haven't changed very much, and that's the kind of thing that's an assumption. So if we're projecting forwards 100 years, one of the big assumptions that we must make is that it's still us writing the software and not them. Because the reality is it's probably going to be them in 100 years' time. So that's one assumption, that they're not doing all of the programming. And it's just a working tool so that we can have this conversation. So let's assume, for the sake of today's presentation, that we're still talking about software that needs to be able to fit inside a human being's head. And that's kind of one of the limitations that we need to work to. So some ideas are more durable than others. So do we think that there's going to be a massive advance that's going to give us orders of magnitude improvement in our ability to build more complex systems based on language? And I would say I don't think so. I don't think so. I think that if you look at the evolution of language, it's not quite as fast as we might think. People certainly like creating new languages. I will guarantee you that the languages in 100 years' time will be different to the languages that are now, that there are now. But in smaller ways than we might think, I think, because of this problem of the level of granularity of writing languages. There are lots of languages, but the level, the productivity that these different languages give us is not a significant, huge step. We might argue about the value of functional programming for some kinds of problems versus OO programming for other kinds of problems, and so on, but we're not going to get a 10x improvement beyond what we're doing now unless we're able to significantly raise the level of abstraction, and the Hollerith machine suggests that maybe that's quite hard. These days, I would argue that most language design is a little bit more about fashion than it is about fundamentals. The principles on which most of our languages are based have been around for a very long time. Functional programming was invented in 1957 with Lisp. OO programming was invented in the 1960s and then developed further through the 70s with languages like Smalltalk, and before that Algol and things. But the principles haven't changed. The difference between, I don't know, a modern OO language or a modern functional language and those early antecedents is relatively small and doesn't allow us to make massive strides in progress beyond what we could do with those other languages. There will be no great leaps in productivity because of programming languages, my guess, in 100 years' time. That's kind of scary in some ways, but I think it's probably true. So my prediction is there's going to be no big move in the level of abstraction. I run a YouTube channel, and one of the videos that I recorded a few months ago on the YouTube channel was about building low-code or no-code software. And one of the things that I observed with my use of those kinds of systems is that it's not typing that's the hard part of the problem. It's thinking about the information and the relationships between the information and having techniques like version control so we can step back to a stable, safe representation. Whatever the nature of the implementation is just as important for something like a low-code system or a no-code system as it is for a system written in a more traditional programming language. The hard part of software development, software design, is about figuring out where we're going to put the information and managing the complexity of the systems that we deal with. It's not the typing. It's not the syntax of the language. So what about frameworks? Frameworks do other things that kind of move us beyond. Again, I don't think that frameworks are going to give us the answer either. Frameworks, if anything, are even more ephemeral than programming languages. So why not? People like writing frameworks too, so there's certainly lots of them to think about, and they come into fashion and they go out of fashion. I did a silly exercise last year. I had a book published this year about software engineering, and I thought it'd be interesting. It didn't actually make it into the book, but I did this exercise where I wrote two versions of the same system. I wrote a very simple CRUD system, and I did one version in a modern web framework, a popular web framework, and I did another one in the technologies of 1996, using Java, JavaScript, HTML, and CSS. There was about a quarter of the code in the 1996 version of the system than there was in the 2021 version of the system. Sure, the new version of the system did more things. It probably did better browser independence than my handcrafted version from 1996. But we haven't made big strides in productivity with these kinds of frameworks necessarily. Why not? I think that most frameworks focus on the wrong stuff. I think that they focus on what often are the easy problems to solve. And the easy things that we can solve, and they kind of ignore those more complex, deeper problems, like the problems of design that I was talking about, and the ability to version control and safely manage information in two different places, and all that kind of stuff. They tend to duck those problems because those are genuinely difficult problems. Less typing is much less important than less thinking. We want to optimize for less thinking if we want to do a better job, if we want to be more productive. So, there may be big steps in frameworks, but I think only in combination with a bigger rethink on design and architecture and programming model. What I mean by that, there's some stuff that I've seen in terms of reactive systems and actor-based systems that I think would make it more toolable in future. And there are some moves, but they're kind of going more slowly than I wish they were. But I think that frameworks on the whole alone are not enough for big steps. What about programming paradigm? What about, the modern favorite, which is functional programming for many people? Again, Uncle Bob says he thinks that maybe we found all of the programming paradigms. I'm not quite sure I buy into that. I'm not quite sure that I agree with that. But it's not obvious where the next big step is in programming paradigm, and there's not an obvious huge difference in productivity between functional programming and OO programming, and I know functional programmers would argue with that, but there's not people that are going 10 times faster, obviously, in building systems. That's not evident to me. There seems to be something durable about the level of detail that we need to specify when we're writing code. Think again back to the Hollerith machine. The fact that the algorithm expressed in SQL didn't look at a different level of detail or a different level of granularity. It looked normal to us. There's something about how we express ideas in terms of the information that our systems deal with that it's really hard to get past that level of detail. There's been loads of attempts during my career to try and raise that level of abstraction. Things like no-code solutions, sort of diagrammatic approaches to programming and so on. And they always tend to stumble at there are some kinds of representations that are just much easier to write in code. It's much easier to write an if statement in text than it is to write it drawing pretty pictures of it, usually. And there are other things like that. So, my risky prediction, this is a very risky prediction. I think that in 100 years' time, programming will still be largely a mix of procedural, OO, and functional. I don't think those things are going away. I don't think that functional is going to supersede OO programming. I think it complements it, is my view. A controversial opinion, I guess. The current fashion, I think, I'm sure that there are people in the room that are vehemently disagreeing with me right now, but the current fashion is kind of downplay the value of object orientation. And I think that's a mistake, to be honest. I think this is largely a religious war. If you look at modern operating system design, the World Wide Web, printer drivers, these are essentially OO concepts. All of the infrastructure that underpins the way that we work was built on those foundations historically in our industry. So to say that OO didn't work is just a mistake. And to say that it doesn't help us to build good systems is just a mistake. It might not be the best kind of thing for some sorts of systems. Functional programming has a big part to play for many kinds of systems, but it's no silver bullet, and it doesn't obviously give us some 10x improvement in terms of the quality and the rate at which we can deliver big, complex systems. So, I think that maybe there might be some new programming paradigms. My guess, if I was to make a guess, is that it seems to me we're missing a way of representing some key concepts that nearly all of us deal with nearly every day in most of our programming languages. The idea of a service. There's no obvious way to delineate the interface to a particular service other than by convention that we adopt within whatever our programming language or paradigm is. Maybe there should be, maybe there could be. Erlang has a better model of that kind of thing than other programming languages. Maybe that could change things, I don't know. When we get to some of the really durable ideas, they are different to what we've talked about so far. They're less about technological detail. I would argue that iteration is deeply, fundamentally a part of what we do. Many of the presentations that I've attended today have talked about the vital importance and the strategic necessity of our discipline being grounded on learning. And in order to be able to learn, we must iterate. We must make progress in small steps, observe those small steps, gather feedback from them so that we can learn. We need to become world-class experts at learning to be able to be good at our discipline. We need to work incrementally. We need to be able to break up the systems and work on them piece by piece and evolve them step by step to grow more complex systems. Nobody builds a world-class complex system, as a genius idea in one step. You build world-class complex systems by evolving them step by step over time. And so working in ways that allow us to do that, working incrementally so that we can make those steps, is vital to be doing a great job, I think. We need to adopt the mindset of working experimentally. If we think about what the kind of granddaddy of being experts at learning is for humanity, it's science. And so we can adopt the ideas and the thinking of science to solving problems in software. I think that's as good a definition as any of what software engineering means. It's applying scientific-style rationalism to solving practical problems in software within economic constraints. I think that's as good a definition as any for software engineering. And so working experimentally is a vital part of this. And it reinforces these other things. Working iteratively gives us the opportunity to experiment on smaller pieces, control the variables, understand the messages that we're getting back from these sorts of things. And then we want to be empirical. We're engineers, not theoretical physicists. So it's not about mathematical precision. It's not about perfect models. It's about adapting to the real world. We're going to get things wrong, and our job is not to ignore getting things wrong and imagine that we're going to do perfect things. That's not scientific. We start off assuming that we're going to be wrong, and then figure out how we're going to detect when we're wrong, and figure out how we're going to correct the wrong things so that we don't make the same mistake again. That's how we build complex systems. We make them better and better and better and better over time. If you want to see a practical demonstration of this, I would advise you to go to YouTube and look up SpaceX's Starship project. Watch them building the space rocket and testing it out in Boca Chica in Texas at the moment. That's practical modern engineering at its kind of limit. It's brilliant to watch. They are changing their minds about everything all of the time. They're redesigning and refactoring spaceships. And you can watch it on YouTube. We need this kind of empirical learning as well as theoretical learning. I don't think these ideas are going out of fashion. These are the things that are going to work. These foundational concepts are grounded in our need to learn and deepen our understanding. Software development is always an exercise in discovery. It's not about thinking immediately, at the start, getting the answers right. It's about trying stuff out, figuring out whether it's getting us further forwards, and discarding the bad ideas and keeping the good ideas. So we need to optimize for that type of learning to do a great job. So my prediction is even if the machines are writing the code in 100 years' time, then they'll be using those techniques. They'll be iterating, gathering feedback, experimenting, taking empirical discovery, working incrementally. Those are the tools of learning, even if you're cleverer than us. So, software in development in 100 years' time will be based on these ideas. These are important, durable ideas. They don't change. They've been true through the history of our discipline, and they will be true through the future of our discipline as well. These are important, and these do represent big steps forward. In 1986, Fred Brooks, the author of the Mythical Man Month, and a famous computer expert, wrote a paper that was called "There's No Silver Bullet." And in it, he said that there was no 10x improvement available in language, process, or technology. There was nothing that was going to give us a 10 times advance in our capability. And I think he was right. But I think he missed something, which is that if you are today, if you are world class, if you're doing the state of the art in software development, I'm biased, but I'd say that's continuous delivery. If you're working at the leading edge of continuous delivery, then there's no 10x for you. There isn't. But that's not where most of us are. There's lots of things that we can do that make us 10 times worse. So if you're in a more average company, there's definitely 10 times improvement available if you take it. And there's data to back that up. You can look at the State of DevOps report and the Accelerate book that describe that's the kinds of practices that I tend to talk about will give you 10 times improvement on many metrics. So we need to eliminate the bad ideas. So we need to find ways of managing things that allow us to eliminate the bad ideas. Some of the other ideas that seem to be more durable than others, and these I categorize in kind of my model of thinking about this as ideas that are focused on managing the complexity of the systems that we build, are ideas like modularity. We want to be able to break big systems up into smaller pieces so that we can understand them, so that we can work on them safely without worrying about what's going on in other parts of the systems. So I think that modularity is an idea that's just not going to go away. Using ideas like separation of concerns, we're making sure that our designs, each part of our design, is focused on doing one thing and doing that thing well, is going to give us a better handle on the design of our software and our ability to make progress. It's going to make it easier to live with over time. And I would say that that's one of the hallmarks of what we would categorize as high quality in software, our ability, our sustained ability to be able to change it. If your software gets harder and harder to change as it grows, then it's not exhibiting these kinds of properties, I would argue. The other part of this is we need to be able to do information hiding. We want to work in one part of the system and not worry about what's going on in another part when we change it. We don't need to worry about that too much. We want to be able to have the pieces appropriately coupled with a preference towards loose coupling so that we can treat with them more independently with one another and maybe compose them in different ways. That gives us some flexibility as a side effect. And we want the parts of the system that are close together, the parts of the system that are closely related to be closely together in the code, so we want to worry about cohesion as well. None of these ideas are surprising. I will guarantee that everybody in the room has heard and thought about these before, but these, I would argue, are the foundational principles of our discipline. These are the things that whatever the nature of the technology that you are using, whatever the nature of the software that you are building, these are the building blocks that will make your life easier. If you think now about the system, a system that you're familiar with, something you're working on right now or something that you've seen in the past, and imagine two different versions of that system, two implementations. One of them is a big ball of mud that has no modularity, doesn't do any information hiding, there's no separation of concerns, it's all tangled together, cohesion's rubbish, and it's all tightly coupled. And there's another one that scores well on all of these properties. Which one's going to be nicer to work on? Which one's likely to be more robust? Which one's more likely to be more fault tolerant, more effective, more easy to evolve over time? And I've said nothing about the technology. I've said nothing about the language or the framework or anything else. These are the foundational principles of our discipline. So, the reason for that is that we must decompose idea into pieces that are small enough to fit into a human head. And these techniques are the techniques that allow us to do that. Software development is about learning and about managing complexity. So our job as professionals is to become world-class at both learning and managing complexity. So my prediction, even if we mechanically extend our cognitive function, and we're almost certainly going to do that over the next 100 years, we will still need to partition problems to fit into our new expanded consciousness, whatever that scale is. So these will still be true. Software development is about learning and discovery. Humanity's best approach to learning and discovery is the scientific method. So, iteration, feedback, incrementalism, experimentation, and empiricism. That's what I mean when I say trying to take the practical learnings of science and applying to software. I'm not talking about Six Sigma levels of precision. I'm just talking about the simple, practical ways of trying to start off assuming that we're probably wrong, trying to figure out how we're wrong and trying to correct it as quickly and as efficiently as we can. Software development is also about managing complexity. Humanity's best approach to managing complexity is to compartmentalize things so that we can deal with one part without worrying too much about what's going on in other parts of the system. Hence, modularity, information hardening, separation of concerns, loose coupling, and cohesion. As I said, I struggle to imagine that there's anybody in this room that's disagreeing with this stuff, because these seem so foundational to me. But we don't often think about it. We don't often think about these as the tools of our trade, but I think that they are. I think that if you start to adopt the mindset of always trying to maximize your scores in these categories, always try and make sure that you're able to iterate fast and efficiently, gathering feedback, working experimentally, building software that's more modular, more cohesive, has better separation of concerns, I think that as an automatic side effect of that, you increase your chances of success. And that's the kind of properties that we'd expect to find from something that we might consider to be an engineering discipline. If whatever it is that we think of as engineering is not allowing us to build better software faster, it's wrong. It's not engineering. Engineering is the stuff that works. Engineering is not about bureaucracy or heavyweight paperwork. It's about the stuff that works. And if it doesn't work, we change it. Continuous delivery. I was one of the authors of the book, Continuous Delivery, so my name's kind of pretty much associated with this idea, I suppose. Do I think this is going to be viable in 100 years' time? Well, you don't know me very well if you don't think that. I'm going to say yes. Absolutely, I think it is. And for good reasons. The reasons why this is true is that I think this is based on a practical application of the kind of reasoning that I've just been describing to solving problems in software. The scientific method is humanity's best problem-solving approach. It isn't going out of fashion, ever. Continuous delivery has at its heart iteration, feedback, incremental design, experimentation, empiricism. The focus on testing in continuous delivery encourages modularity, cohesion, separation of concerns, abstraction, and loose coupling. So, my prediction is, even if the machines do write the code, they're going to adopt continuous delivery to do it in 100 years' time. I did manage to do it in half an hour. There you go. So we've had some time for some questions, if there are any questions. Thank you very much.